Welcome to the presentation of our demonstration paper on multi-agent pathfinding for indoor quadcopters. My name is Pavel Surinek, and this is mostly work of my student Matouš Kulhan, and we would like to present outcomes that he achieved in his bachelor thesis. In this work we are trying to execute plans for multi-agent pathfinding with small indoor quadcopters. Multi-agent pathfinding is the task of finding non-conflicting paths for a group of agents. This is an important abstraction for tasks that arise in multi-robot systems, warehouse logistics, and so on. In our case, we are executing plans with Crazyflie quadcopters. This is small programmable quadcopters, and they are coupled with a simple localization system. Our aim is to develop execution platform for multi-agent pathfinding plans. There is a relatively big gap between ideal plans produced by multi-agent pathfinding algorithms and real environments where real robotic agents act. To test the difficulties with the transition of plans to real environments, we believe that this platform can be useful. We assume that it can be useful for researchers and practitioners who are developing variants of multi-agent pathfinding that are to be deployed in real-life scenarios on real robots. We also try to support research of bridging discrete multi-agent pathfinding and continuous real world. And our platform can be useful also for educators to demonstrate the importance and difficulties of multi-agent pathfinding and planning acting chain in general. The main feature of our execution platform is that it's a modular architecture. It can integrate various MAPF solvers. It can integrate various localization systems. Currently we are using radio measuring of distance between several anchors and the quadcopters, but also optical localization sensors can be used as well. The benefits of our execution platforms with quadcopters is that quadcopters enable quite complex movements in three-dimensional space that supports execution of relatively complex multi-agent pathfinding plans. The important feature that is quite innovative with respect to multi-agent pathfinding is that movements of quadcopters are continuous. So we basically support continuous variants of multi-agent pathfinding in our execution platform. The concrete transformation of general planning acting scheme to our case of planning acting scheme for MAPF mostly consists of a transformation of plan produced by some multi-agent pathfinding algorithm to a flight plan for quadcopters. This transformation is done by a Python script that controls quadcopters. As for algorithms, we are using continuous time conflict-based search with some adaptations for quadcopters. This adaptation consists in adding protection zones above and below quadcopters, because in case of quadcopters they should not approach vertically. We used our execution platform for experiments focused on comparison of expected ideal plan with real execution. Here we can see two experiments. The first experiment consists of two agents, and the experiment compares the ideal plan produced by continuous time conflict-based search with real trajectories executed by the agents. In the second experiment we have more agents, actually 4 agents in more complex scenario, and these experiments takes place in a real setting, which we will show in the demo. This is our demonstration. You can see 2 quadcopters following trajectories computed by continuous time conflict-based search. This experiment takes place in our flying area of size 2 times 2 times 2 meters. The flying area is equipped with sensors, so we can localize the quadcopters in the real time, so they can augment their position to follow the trajectories. And we tried different experiments of various complexities and various complexities of avoidance between the agents. You can see that the protection zone consisting of cylinder below and above the quadcopter has some role in these scenarios. This is more complex scenario consisting of 3 agents, and actually we plan to take with ourselves more compact version of localization system. So this will be much smaller than this equipment. Quadcopters themselves are very compact, so they can be easily taken, and this is the most complex scenario consisting of 4 agents and very complex avoidance between them. Our main finding from these experiments is that we needed only little adaptation of the original continuous time conflict-based search algorithm to produce plans that can be directly executed with real quadcopters. In a broader sense, our execution platform can serve for testing plan execution for different variants of multi-agent pathfinding. That's it. Thank you for your attention.